Okay. Uh, so what I'm doing today is meant to be, we're starting deriving consequences of theory in the last lecture. So we have this result. So that, well, basically information about the eigenvalue support, and we can use that to rule out perfect state transfer in many cases. So one consequence, for example, would be that you don't get PST on a long path, because we've showed there's only finitely many graphs with connected graphs with maximum valency 2 that emit perfect state transfer. Now, something a lot stronger is true, and we'll get to that. But so the point is, we have a general result, but it has a lot of interesting consequences which I'm going to work through. The first one is the question about how long you have to wait to get perfect state transfer, which seems interesting in its own right, but it has other consequences as well. So we'll go on to that. So there's time to perfect state transfer. Now, the point is, if we have transfer from A to B at time tau on some graph, then we have this vertex state is equal to this mess. Okay, so this is just UT E sub A transpose U minus T expanded. And then because this is real and this is real and this is real and this is real, this has to be real. And so that tells us that this exponential here is plus or minus 1 for any pair R and S in the eigenvalue support. And to make our life a little easier, we'll say, well, if that's true, then this is true, that at time 2 tau we get equal to 1. And so in other words, this is I'm just restating the proof that if we have PST at time tau in the real case, when everything inside is real, then we get periodicity at time 2 tau. And so that's what I'm going to work with. So the question is, what's the minimum period? How long do you have to wait to get back to your starting point? Okay. And it's at least tau such that tau theta, tau times the eigenvalue difference is a multiple of pi. Now this is understandable, assuming here that this is for all everything in the eigenvalue support. So there's a condition there. Now, the first thing is that instead of using all the eigenvalue differences, you only need to use the differences of the form theta 0 minus theta r, because you can get any one of these differences as a difference of two of those. So we only need to about this. So now we only have essentially, well, if there are m eigenvalues and eigenvalue support, we only have m differences to worry about. And so we need this to be an integer multiple of pi for all r. Okay, and so we can translate that. We know that in general, theta can be written in this form as an integer a plus, should be actually there's a t, it should be a half in there, isn't there? Oh, this is interesting. So we're going to do better today. So if we have that, then the eigenvalue differences are, yeah, okay, then theta 0 minus r. And so this would be r pi on 2. So that's going to, yeah, better. Now, so, okay, so that means, and so I'm thinking of this as being, as being the spectral radius. Not that it particularly matters, but there's no reason not to. You know that the spectral radius is in the eigenvalue support because the corresponding eigenvector is positive. And so that means that the spectral radius is always in the eigenvalue support of a vertex state, and we get these differences. And so the time to perfect state transfer is going to be 2 pi, almost 2 pi. Okay. So it's not obvious at this point, but in a certain sense, that's pretty quick. Okay. Now, if that's another bound, and so we have that. We'll see later. We'll discuss what happens on cases where we don't have perfect state transfer and how close we can get. And you can get quite close, but you have to wait a much longer time than that. Again, so the point, but still we have this bound. Okay, and I want to do something with it. And this comes up to heading what the physicists like to call monogamy of PST. So it says if you have PST from A to B in some graph, vertex states, and PST from A to C, then B is equal to C. Now this actually holds for real states, but so we won't. I'm not going to worry too much about that. So the lemma is due to Alistair K, and as I said, this is what the physicists will refer to the monogamy of vertex state transfer. So you can't get, you don't have to worry about transfer. If you get perfect state transfer, there's only two vertices involved. And the basic idea is simple enough. I mean, if you get perfect state transfer between two vertices, then it follows that those two vertices have the same eigenvalue support. You might need to go away and think about that for a little bit, but it's not difficult. And if they have the same eigenvalue support, the next thing is that the time to PST just depends on the eigenvalue support. And the period is just depending on the eigenvalue support. Okay, so the issue is if I have PST from A to B and PST from A to C, then the PST, when I go, you must go from the time it takes to get from A to B must be the same as the time you get from B to C. And now lots of things can happen in quantum mechanics you don't expect, but you can't get transferred to two different states at the same time. Okay, so if you're at time tau, you're on some state, and so because the time is determined by the eigenvalue supports and the eigenvalue supports don't change, we get monogamy. So it's an important fact that you don't have to worry. If there's PST, it occurs to most one other vertex. Now this works more generally. This works for real states. It's not actually. I was thinking about vertex states back here, so and that's fine too. But this holds fairly generally. Okay, so we have this monogamy of PST, and it's a consequence of this time information. Okay. Now, the next thing I want to discuss, and again, we're looking at special cases now of what we can learn from our characterization of the PST. And so if it turns out for bipartite graphs and regular graphs, we can say something a little stronger. So instead of getting eigenvalues and the eigenvalues of order of constants in the form half A plus B root delta, we just get integer moles of A plus B root delta. We just get integer moles of square root of delta. So we get the eigenvalue support, the eigenvalues, the eigenvalue support have a simple constructor. Basically, the square of any eigenvalue in the eigenvalue support is an integer. Okay, that's a little weaker than what we prove. So I'm going to look at bipartite graphs and then at regular graphs. Now, if X is bipartite, the eigenvalue support of a vertex is closed under multiplication by -1. Now, the proof in the notes with Gable is just wrong at this point, but we'll have to fix that. But anyway, so here's the proof. So now the thing to bear in mind is, so for a bipartite graph, the spectrum of the graph is closed under multiplication by -1. If theta is an eigenvalue, then minus theta is an eigenvalue with the same multiplicity. But I'm saying something a little different here. What I'm saying is the eigenvalue support is also closed under multiplication by -1. And so if theta belongs to the eigenvalue support, so does minus theta. Okay, so that's what we have to prove. And the machinery is we take the diagonal matrix with diagonal entities 1s and -1 such that D is equal to -A. So I use this when I proved the fact that the spectrum of a bipartite graph is closed on multiplication by -1. So you've seen that before. And in that context, we also saw that, well, D maps A to -A, and it maps the idempotent corresponding eigenvalue theta to the eigenpotent corresponding eigenvalue minus theta. Now, what this D is doing to the matrix is you've got this partition into the white vertices and black vertices. So you've got a 2x2 block matrix. And what D is doing, or what this is doing, is it's taking the off diagonal blocks and multiplying them by -1. Okay. And so you go from E theta to E minus theta without any particular problems. And from that, you see that if E theta applied to E sub A is not 0, then it follows that E minus theta applied to E sub A is not 0. Now, you may need to stare at that one for a little bit, but it's okay. So, yeah. And now I'm not claiming anything about, I'm proving this for vertex states. I make no claims about what happens in other cases. In fact, it's going to break down some other case. But in any case, so if we're bipartite, then not only is the spectrum closed on multiplication by -1, but so is the eigenvalue support of the vertex. Okay, so that's fact number 1. Now, well, I'll show you the notes. So now assume our graph is bipartite, and we've got a vertex A is periodic. Now it's the claim is the eigenvalue support of that vertex consists of integers or integer models of square root delta for some square free integer delta. In fact, we always take it like this. We just as easily say it consists of integer models of square root delta for some square free integer delta and allow delta to be equal 1. And then you get the integer case, the delta case. But anyway, that's just fussing. So this is the claim. We don't get this. In particular, two things are happening. One is that this constant A is not there. It's equal to 0. And the second thing is we don't get the division by 2. Okay, so let's assume that the eigenvalue support contains a non-integer eigenvalue, which is the only case you need to worry about. Then each element in S can be written in the form, and I got to write this first time. So we're written in that form. So fixed integer A, some integer B sub R, delta square free. Okay. Now, since S is closed on multiplication by -1, we see that A is equal to 0. Okay, and so if okay, so A is equal to 0. So now we know that every eigenvalue is the form B times square root delta over 2. Now, B times square root delta is an algebraic integer, but nobody knows what B times square root delta over 2 is, so we need to work something out. So if we have theta equal to this, then theta squared is B squared delta over 4. Now, theta is an algebraic integer, and so theta squared is an algebraic integer. And so this is an algebraic integer. And so since it's rational, we again use the argument that this must be an actual integer. Okay. Now, in that case, since delta is square free, it could be divisible by 2, but it can't be divisible by 4. So 2 divides B squared. And so 2 divides B. And so the B over 2 is an integer. So B is even. Okay, that's a B there, not an H. So B is even, and so we get the claim. Okay, so so for bipartite graphs, we have this simplification that the eigenvalues. Now this is nice. I mean, the path on 3 vertices, its eigenvalues are plus and minus root 2, 0, and root 2, and it admits perfect state transfer. So clearly, integrality is not necessary, but the what's happening on P3 is in some sense the worst that can happen. Any questions at this point? So okay, so now I want to deal with regular graphs. And I'm going to do this in slightly greater generality. So if I have a regular graph with valency k, then k is the largest eigenvalue. Okay. The assumption I'm going to make is I'm dealing with a connected graph, and the spectral radius is an integer. So it doesn't have to be a regular graph. It just, the important point is the spectral radius is an integer, and it's probably going to be an integer k before very long. Okay, and so then under that condition, we're going to prove that if we have a periodic vertex A in our graph, then all elements of this eigenvalue support are integers. Okay, so that then is a condition, a necessary condition on the eigenvalue support for a regular graph which admits perfect state transfer. Okay, so okay, so we're going to prove this. So assume by way of contradiction that theta lies in the eigenvalue support of A, and that theta is not an integer. Okay, so then theta is a quadratic integer. So by the theorem, we're saying theta is half A plus BR root delta on 2. It satisfies a quadratic polynomial with integer coefficients, and in particular, there's a field automorphism which maps theta to its distinct algebraic conjugate. You've got a quadratic integer. The quadratics have 2 roots, so those 2 roots are conjugates. So there's a field automorphism which maps theta to its conjugate. And so I'm going to denote the conjugate by theta bar, which confused me no end when I was going through the notes earlier. But so it looked like a complex conjugate, but it's not a complex conjugate. Okay, it's just the algebraic conjugate. Okay, so the algebraic conjugate of root 2 is minus root 2. Okay, so that's just a notational point. And so we have this field automorphism that maps an element to its algebraic conjugate, and in particular, it maps theta to theta bar, which is not equal to theta. That's really all I care about. So, well, I've said that we're going to assume that theta bar is not equal to theta. Now, by the ratio condition, we get this. And now the thing to observe is that row, which I hope to look like a row and not an E, that row is the spectral radius and it's an integer. So if I take the algebraic conjugate of this algebraic number, it turns into theta bar minus rho over theta minus rho. Rho doesn't change because it's an integer. And so we get this, so we get these things equal. Okay, and so we just do the obvious, multiply things out to get rid of the ratios, and you get that theta minus rho squared and theta bar minus rho squared are equal. And so then you take the difference of two squares, x minus y, x plus y, and you get this is 0. Now we've assumed this is not 0, so this tells us that rho is equal to half of theta plus theta bar. But rho is the largest eigenvalue, and so neither theta nor theta bar can be greater than rho, so what we're getting is that rho is equal to theta. But rho is an integer and theta is not. And so that's the end of the argument. Okay, so what I've actually proved. So this proves that, well, I don't have any, I can't find an element in the eigenvalue support whose algebraic conjugate is distinct. In other words, all the things in the eigenvalue support are integers. Now, for this, we do need the graph. I mean, the other thing, the graph must be connected because you could have several components. And this just tells you that the component containing A, the support in the component containing A would be all integers. Okay, so so we have this condition. The one reason we're fussing a bit about this is, well, we're trying to understand perfect state transfer. So we pick some interesting graphs and pick some interesting vertices and try and cite if there's perfect state transfer. Okay, so you got the graph, and the question is, are there any interesting vertices? Well, the first thing you say, well, then I've got to test whether I look for periodic vertices and then fuss about PSD between those. Okay, so I'm looking for periodic vertices. And so that means I get the vertex and I have to look at the ratio and I have to look at the eigenvalue support. Now, it's a lot easier to decide if the elements of the eigenvalue support are just worst square roots of integers than to go through the A plus B root 2. So any simplification like this, for one thing, it makes the searches easier and faster. Okay, I mean, it's other consequences as well. It's kind of interesting that for regular graphs, there's a stronger condition. So on the eigenvalue support, so the implication might be that perfect state transfer on regular graphs is harder to arrange. Or maybe, I mean, so it raises various questions. Now, again, any questions from you guys? Okay, so this is in a certain sense, well, it's not unrelated, but you can think of it as a newish topic. So I want to talk about controllable vertices in graphs. Okay, and so you can view this. This is the straight algebraic graph theory, but then we'll be applying it to get some more information about perfect state transfer when we get towards the end. So I have to talk. Well, I don't have to, but I'm going to talk about controllable vertices and controllable things in graphs. The terminology actually comes from control theory, but you don't need to know that, so we can forget about that. So if I have a graph on n vertices, and I pick a vector z, I'm going to construct this matrix. I just apply the powers of A to Z. Okay, so I get an n by n matrix, and I'm calling that the warp matrix of Z. Now, it might be obvious why I call it warp matrix, otherwise we'll see more as we go on. So we get this matrix. So this is an n by n matrix. And the definition is that the pair, the adjacency matrix, and the vector is controllable if this matrix is invertible. Now, this is just a definition. This is the definition I choose to use, so there's nothing to argue about. And I said on many occasions, definitions aren't explanations. It doesn't have to make sense. It just has to be easy to use. And this is fairly easy to use. I mean, you could form that matrix and get us determinate. And so that's an easy test. Now, in the cases that concern us, Z will be the characteristic vector of a subset of the vertices. So it's a 0, 1 vector. And it'll usually either be just the characteristic vector of one vertex or the entire vertex set. Now, I guess you could take cases with bipartite graphs where S was one of the color classes. That could be interesting. I just never thought about it. Okay, so these are the two cases we can care about. And so now well, yeah, why am I fussed about controllable? There's some couple of deep papers by Bazad and Turi that depend on deep work by Tao and Vu that imply that almost all graphs are controllable. So for almost all graphs, the pair A, comma, the vertex set is controllable. Okay. Secondly, for almost all graphs, all the pairs X, comma, V, where V's a vertex in the graph, are controllable. So the idea is, in a sense, that almost all graphs have this controllable property. So it's something that's very common. Okay, and we're going to use it to rule out perfect state transfer, and then we're going to conclude that for almost all graphs, you don't get perfect state transfer. So it's going to give us information about or non-existence of perfect state transfer. Okay, so we want to say anything more about that. So you can, in some sense, view controllability as kind of an analog of being a random graph. Except the way I like to put it is, if I give you a graph and say, is this random? There's nothing you can do. If I give you a graph and say, is it controllable? Then you can construct the warp matrices and test. So it's a recognizable property. You can verify it in polynomial time. And in many cases, for a lot of things you prove about random graphs will hold for controllable graphs without any extra work, or little extra work. Okay. So this again, this terminology. So instead of saying that the pair adjacency matrix, comma, vertex U is controllable, I'll just say U is controllable. And similarly, saying pair A, comma, the vertex is controllable, I'll just say X is controllable. Now, I won't be talking about controllable graphs much anyway, so it's only the controllable vertices that concern us here. And this is an adjustment to the warp matrix, so I write W sub S rather than W sub a vector. But in this case, we're just using the characteristic vector of S as our starting vector. Now, I think I got this right. The point is, if you're working with a vertex, we're working with a subset, the IJ entry of the warp matrix is the number of walks in the graph of length J minus 1 that start at the vertex I and end in S. Okay, so the point of this is not that I've got the I's and J's all in the right place. The point is that it's determined by walks in the graph. Okay, and so it's reasonable to call it a warp matrix. Okay, and that can play a role, and it won't affect us much for what we're doing now, but in other use situations, it's actually relevant. Okay, so we've got controllable vertices, and I'm promising you, according to Bazad and Turi, there are lots of them. Okay, and so I need to establish some properties. Okay, now the random graphs are asymmetric. Probably, probably that a random graph has a non-trivial automorphism goes to 0 as the size of the vertex that goes to infinity. Now the same thing is true for controllable graphs. Okay, if X and S is controllable, then any automorphism of X which fixes a set S is the identity. Okay. Now, an interesting case here is where the graph, actually, I didn't quite what I said before. If I take the case where I take the pair X, comma, the vertex set of X, then any orbital graph must fix the vertex set. And so you conclude if the graph is controllable, its automorphism group is trivial. Okay. The other thing you would learn is if the vertex is controllable, then any orbital in the graph which fixes that vertex is trivial. Okay. Anyway, let's go to the proof. So I'm assuming I'm working in permutation matrices. So I've got a permutation matrix P, and it commutes with A. It's an automorphism of the graph X. And I'm using E sub S for the characteristic vector of S, the subset we're working with. Now, P fixes the subset as a set if and only if it maps the vector E sub S to itself. Okay. And so now we just check, we look at P, A to the R, E sub S. Well, P commutes with A to the R, and now P fixes E sub S, so you get that P applied to A to the R, E sub S is equal to the A to the R, E sub S. And that implies that P maps the warp matrix to itself. But if the warp matrix is invertible, then P is the identity. Okay. So, I mean, this is reasonably straightforward. I think it's, it's quite straightforward. So we've got this concept of controllability, and we've already got, we get these interesting consequences without much effort. And by Bayes-Out and Turi, they say that, you know, well, almost all graphs are controllable. So that tells me that almost all graphs are asymmetric, which Erdős and Renier proved many years ago. But their point is they proved that random graphs are asymmetric, and that's good too. I'm not fussing too much. But as I said, if I give you a graph, you can't tell if it's a random graph or not. The question makes no sense. So it's an interesting, and so it has a number of uses. Okay. So now I want to get to a more, this is another consequence of controllability, and this is a bit more surprising. Now, to do that, basically I'm proving a result about tensors, but I decided to be kind and not tell you that, so we'll just prove what I need. I might say a bit more about that in a minute. I need a lemma. The lemma says I have a set of vectors, in R to the n. Okay, and I'm defining the outer products. I've got m vectors, so I've got m squared outer products. And then the lemma I want, it says simply that the S span a subspace of dimension k in R to the n if and only if the matrices Qij span a subspace of dimension k squared in the space of invariant matrices. Now, yeah, it's easy enough to stare at this for a bit and decide it's not surprising, but we'll go through a proof. So, I mean, to prove it, it's enough to show that if the vectors v1 through vm are linearly independent, then these matrices are linearly independent. Okay, and so since there's m of these and m squared of these, we get the result. Okay, so that's the, now the first step is to note that if the v1 through vm are linearly dependent, then these matrices vi, w transpose are linearly dependent. And so then so clearly the if and only if part, so half of that is done. And I can never tell which is if, which is only if, so I've done one half. So we're looking at the other half. We're assuming that v1 through vm are linearly independent, and we want to show that the outer products, the m squared outer products, are also linearly independent. Okay, so the trick we use, or I don't like calling it a trick, is use something which I call a dual basis. So I've got a set of vectors in R to the n, not necessarily a spanning set, just some set of vectors. And I wanted to find something which I call a dual basis. So it's going to be a collection of m vectors, w1 through wm, such that that vi transpose times wj is equal to Kronecker delta. So if in matrix terms, so we're drawing out, that would say I'd have v1 transpose vm transpose times w1. Now, the point about this is, okay, now this is just a matrix equation, and if the columns are fully independent, then you can find W's that work. So any set of linearly independent m linearly independent vectors has a dual basis. And in fact, in a certain sense, sometimes the nicest way of proving that some vectors are linearly independent is to prove that they actually have a dual basis. But that we don't really need to know that. So to find a dual basis, that's a set of vectors that satisfies that. So now we go to the actual proof, which is basically two lines. If there were scalars such that the outer products were linearly independent, then I'm going to use the dual basis. That probably should be a transpose there. I'm being fussy. Yeah. So I just look at, I've got 0 is equal to this. Okay, and I've wrapped it by WR transpose and WS, that doesn't change it. And so now I pull the things through the summation sign, and I get 2 copies of the Kronecker delta. And so the only one term survives, and what you're staring at is the RS entry of A. Okay, and so if this is 0, then ARS is 0 for all R and S, and so they're linearly dependent. Okay, okay, so that's the end of the proof. So the point is, if the vectors v1 through vm are linearly independent, then the m squared outer products are also linearly independent, which is kind of nice. You've gone from independent set of size m to an independent set of size m squared. which is not something you usually do with linear algebra, but there it is. And so this leads to a nice corollary, and this is what we want. If S is a subset of the vertices of X with case vector Z, then X and S is controllable if and only if the matrices if these matrices form a basis for the n by n matrices. Now, the proof is simply to note that the S is controllable if and only if these vectors for I equals 0 to n minus 1 are linearly dependent. They're the columns of the walk matrix. So this is an immediate consequence of the previous lemma. Now, so you get an explicit basis for the space of n by n matrices. Now, your favorite basis will be the matrix, which is E sub ij, which is one, the ij position and 0 everywhere else. But this is giving you alternative bases. The other consequence, and maybe I'll write this out, corollary of this, if S is controllable, the algebra generated by these two matrices equals this all works over the complexes too, but there's no reason to worry about that for what we're doing here. So now, if S is equal to the vertex set of X, then ZZ transpose is equal to J. Okay, and so, I mean, so if S is controllable, then these matrices generate the space of n by n matrices. One consequence of that is, suppose you've got an automorphism, which gives another proof of something we've already seen. Suppose I have an automorphism of X, okay, given by a permutation matrix P. Well, P commutes with A, because that's the definition of automorphism, but it also commutes with J. Every permutation matrix commutes with J. And so, but if you commute with A and you commute with J, then you commute with anything in the algebra they generate, any sums of products of A and J. So that means if you commute with A and J, you commute with every matrix of order n by n. And the only permutation matrix that computes with every matrix of order n by n is the identity. So this proves that a controllable graph is asymmetric, and in fact, the same argument essentially proves you that if the automorphism, if a set S is controllable, then the automorphisms which fix that set are trivial, because in that case, this still generates. You have to, in that case, the permutations have to compute with both terms here, and that gives you the result. Okay, so but it's still somewhat surprising that you want to get the set of all n by n matrices. So you pick a graph and you take the all ones matrix, and lo and behold, you got the full matrix algebra. Okay, and so one consequence of this is, since because of the result of Bayes-Adam and Turi, is that for almost all graphs, if you take the graph and the all ones matrix, they generate the full algebra of matrices, which is possibly not what you expect. You tend to think, well, we've just got this 0, 1 matrix A, and we've got this J. It's not much. It's only rank 1. But in most cases, that's enough to give you the full matrix algebra. Now, I find that interesting. It's not directly related to the quantum walks that I see, but so again, so any questions? Like, what's the time? 14:04. Yeah. My aim now is to prove that controllable vertices cannot be periodic. Okay, and so there's a lemma in here which, well, it does what I need. So that's all I can say for it. And it's not. No, I find the proof interesting. So the result is that if we have a graph on n vertices, and I'm using sigma to note the maximum distance between the eigenvalues of X, then sigma squared is at most 12, is less than 12 over n plus 1. Now, if two eigenvalues are equal, then sigma is 0. So I'm going to have eigenvalues theta 1 through theta n. And if theta I is equal to, if two of them are equal, then the sigma is 0. Okay, well, that's all right. There's nothing wrong with so the point is, this is going to be most interesting when there aren't any, when the eigenvalues are simple. Okay, so that's the theorem. So I'm not sure I really need to do this, but there's no harm in assuming I've got the eigenvalues in non-increasing order, theta 1 through theta n. Okay, and now there are eigenvalues adjacency matrix. Now I'm going to work with this matrix, which is you can view it as a signed Cartesian product. If you think of this in terms of quantum walks, then this is Alice doing her quantum walk in the usual way, and this is Bob doing his quantum walk running time backwards. But we won't go there. So this is a signed Cartesian product. And so I think I asked you to prove that the eigenvalues of the Cartesian product were the sums of the eigenvalues of the term, and the same argument gives you the eigenvalues of M, the differences. So I know the eigenvalues of this guy, they're the differences of the eigenvalues of A. And so this will have 0 as an eigenvalue of, multiplicity n. Okay, so that's, okay, I mean, that's not a problem. It turns out that I'm not too concerned about M. What I'm concerned about is M squared. And so here, I've actually done the hard work for you. I've worked out M squared. There's no particular problem. If I let M be the number of edges in the graph, well, what I plan to do is take the trace of both sides here. And the thing to notice is that the trace, well, first thing, the trace, I guess it's worth writing this down. Trace of A chronic of B equals trace of A times the trace of B. Okay, so what can we say in way of preparation here? This is going to have trace 0. So I can ignore that. Now, the diagonal entries of A squared, the ith diagonal entry of A squared is the valency of the ith vertex. So the diagonal entries of A squared is just the valencies. And so the trace of A squared is just the sum of the valencies, which is twice the number of edges. And don't forget the trace of the identity is n, not 1. I had some trouble for a while. And so the trace of this is going to be n times twice the number of edges. And this will be the same. And this is 0. So we report the calculations here that the other point is the trace of M squared is the sum of the squares of its eigenvalues. So that's the trace of M squared. Okay, as I said. And by what I just said before, this is equal to 4M times N. So I have an expression for the sums of squares in terms of the number of edges and number of vertices. Now, the other assumption we've made here is that the difference between theta I and theta j, well, the difference between two eigenvalues is at least sigma. Now, the difference between theta 3 and theta 1 is the sum of the differences theta 3 minus theta 2 plus theta 2 minus theta 1. So we get this. Now, this is where I'm using the fact that my eigenvalues are in order. Okay. And so then that means the sum of the squares of the eigenvalues is bounded below by this, the square of the difference, times the sum of the squares of the numbers, sum of the differences, squares of the differences numbers 1 through n. And in the notes, I was kind of worked it out. And so that's this sum is equal to this. And I guess if you want an easy exercise in induction, you can go and prove that. And it's also worked out in the notes. So I have, what we get then is that sigma squared times this stuff is less than or equal to 4mn. And the number of m is number of edges in the graph. And so the graph's got n vertices, there are most n choose 2 edges. So that's 2, we get something just depending on n. And so this then proves, after a bit of rearrangement, that sigma squared is less than or equal to 12 on n plus 1. we're almost there, except in the statement of the theorem lemma, I had a strictly less than here, not less than or equal. But that's not too hard. If this were tight, then the number of edges in my n vertex graph would be n choose 2, and so my n vertex graph would be the complete graph. And for the complete graph with at least 3 vertices, sigma is 0. So provided I don't fuss about things, I may have excluded it. Yeah, I probably should have excluded. But yeah, so n at least. Let's write in here just so that I know. Yeah, just so it's in the notes. Okay, so so that proves the bound, so that sigma squared is less than 12 on n plus 1. And so that's the theorem about distances between eigenvalues. And so this is just a comment about getting the strict inequality and having the time. And so now the theorem is if you have a kinetic graph on at least 4 vertices and some vertex in X is controllable, it's not periodic. Okay, so as ever, we let n be the number of vertices of the graph, and we assume by way of contradiction that A is controllable. Okay, so that means that the warp matrix in this case is just the powers of A applied to E sub A, and controllable says these are invertible, so this is invertible. Now, every power of A is a linear combination of the spectral idempotents, and so the vectors EBR sub EA form a basis for the Cole space of the warp matrix. Okay, now this has got dimension n. If these guys form a basis, there must be n of them. So we're going to have n distinct eigenvalues, theta 1 through theta r, and for each eigenvalue, the E sub A is not 0. So the eigenvalue support of the vertex A is the spectrum of the graph, and the eigenvalues of the graph are all simple. Okay, yeah, okay, so if we have a controllable vertex, then we get this statement that the eigenvalue support of a vertex, that vertex is equal to the spectrum of the graph, and the eigenvalues of the graph are all simple. You can prove that a controllable graph can have only simple eigenvalues. That's maybe might even be worth making into exercise. Now, we assume A is controllable. Now we used our characterization of PST. We know that because we have this expression, we know that the eigenvalue support consists of quadratic integers, and the difference of any 2 is at least 1. Okay, so then so we have sigma equals 1 in our bound, sigma squared less than 12 over n plus 1, and so that implies that n's at most 10. So if a graph has more than 10 vertices and has a controllable vertex, that controllable vertex is not periodic. What happens if n is less than 10? In the notes, I fuss a bit about the case n equals 10 because Sage is a bit slow on the 10 vertex graphs, but 9 vertices and below, you can do it with a computer. So I'm just going to be optimistic and say use a computer to clean off the small cases. Okay, yeah, so the other remark I want to make is you can test one test to control. Well, you could if you want to actually test whether vertex is controllable, you could compute the warp matrix. Now that involves you doing n matrix multiplications, and now I have a set of proverbs for numerical linear algebra. Actually, computing powers of computing the warp matrix isn't too bad. You just take a vector y and keep hitting it with A. But one of the general principles of numerical linear algebra is that multiplying matrices is an expensive operation, and you don't want to do it. It takes time n cubed to multiply 2 matrices. You can solve systems of linear equations in time faster than n cubed. So in terms of linear algebra, an algorithm that runs in time n cubed is slow. Okay. Now the point is that you can. So Now, as I said, we're in the business of looking for controllable vertices and things like that, and so we're just using stage, and so we want efficient algorithms. And so I'm just remarking that one test for controllability is that the vertex stays controllable if these two polynomials are co-prime. Now, the characteristic polynomial routines are quite fast. They will work on graphs with hundreds of vertices. Okay, and similarly, the testing co-prime is not complicated. So this is a useful characterization of PST. I mean, it's got other interests, but as I said, it makes calculations easier, and it's also it's useful if you're trying to decide whether the vertex is periodic or not. It's nice if you can do your test in exact arithmetic. Okay, and so certainly you can do all this over the inches, so everything's in exact arithmetic. You're not trying to decide whether two floating point numbers are equal. Okay, now the floating point calculations are important and useful, and computer scientists tend not to want to use them, so you can say try to stop you doing it most of the time. But there's nothing wrong with using floating point calculations, but there are times when you want more precision. And in cases like this, the point about this is it's a condition which works it works over the inches. A good comparison case would be to try to test whether a vertex is periodic. Now, the way with the theorem comes, it tells you if it's periodic, the vertices of the form a plus br root delta on 2. Now, you could try and do that. So, if you think about just implementing that, you will probably decide that there must be better things you can do with your time. Okay, so that theorem is not necessarily giving you the most efficient way of deciding. Now, you can decide in polynomial time, Gabriel and I proved that, you can test in polynomial time whether a graph emits steady state transfer. Okay, but you need to, it needs a little bit of thought before we got a paper out of it, so it's not trivial, but so you can test these things in polynomial time, and you can do them exact arithmetic in most cases. Now, before too long, we'll be talking about various relaxations of perfect state transfer, in particular one called pretty good state transfer, which is something an approximate version. And for that, we have real problems. We don't have polynomial time algorithms for detecting it. Okay. Now, as far as this course is concerned, I'm not going into those details. It's far beyond what we need. And are there any questions? I'm about to stop.